So welcome back to this lecture 16. We are now going to discuss the Chinese remainder theorem. Before we state the theorem, let's recall the definition of group isomorphism. So we said that groups G and H are isomorphic if there exists a bijection psi from G to H such that psi of alpha star beta equals psi of alpha O cross psi of beta for all alpha beta in G, and here star is the binary operation in G, and O cross is the binary operation in H. Okay. And this bijection psi was is called an isomorphism. It's an isomorphism between the groups G and H. Okay. And when we have these groups G and H which are isomorphic, we write G. The notation is this. So we denote this by, say, if G and H are isomorphic, groups, we write G this isomorphic to H. So this is the symbol for the isomorphism. Okay, so so this is just the recall or the definition of group isomorphism. And again, before we can state the Chinese remainder theorem, we just need to observe just one more observation, which is that if you have two groups, or you can say fact or observation, given groups G and H with operations star in G and O cross respectively, O cross in H respectively, we can define a new group as follows. And the group will be on the Cartesian product of the sets G and H. And the binary operation on G cross H, this Cartesian product, will be coordinate wise operations in the groups G and the groups H. So the group operation, so the set G cross H is for completeness, is the set of all ordered pairs. G comma H with little g in G and little h in h. So this is the set, and the group operation will give it another notation. We'll say just or a circle of G cross H is defined as GH circ G prime H prime equals G star G prime. So the first coordinates in these two ordered pairs are both from G. So star is defined on G. So you just take the result of the binary operation between G and G prime, and then you take H and O cross H prime. Put that as the second coordinate. So if you have two groups G and H, you can define a new group on the Cartesian product of G and H, on G cross H. And for the operation on G cross H to make sense, we just define it coordinate wise. So now we are ready to define the Chinese remainder theorem. So the Chinese remainder theorem, just shortened as CRT sometimes, it states that the statement is as follows. So let n equals pq, where p and q are integers greater than 1, which are relatively prime, where pq belong to z, p greater than 1, q greater than 1, and GCD of pq equals 1. So you have integers greater than 1, which are relatively prime. Then there are going to be two group isomorphisms. First is Zn, the group which on the integers 0 to n minus 1 with addition modulo n as operation is isomorphic to Zp cross Zq. So Zp is the group of the integers 0 to p minus 1, and Zq is the group. So Zp is the group with integers 0 to p minus 1 and addition modulo p. And Zq is the group with of the integers from 0 to q minus 1. Again, addition modulo q here. So the Cartesian product of these two, the group which is formed by the Cartesian product as per our definition we had here, so that is isomorphic to Zn. So that is the first part of the theorem. And Zn star is isomorphic to Zp star cross Zq star. Okay. So again, Zn star is the set of integers from 1 to n minus 1, which are relatively prime with n. So we discussed that in the first part of this lecture 16 extensively. So I won't repeat it here. Similarly, Zp star is the integers from 1 to p minus 1, which are relatively prime with p, and Zq star is the integers 1 to q minus 1, which are relatively prime with q. And furthermore, the theorem also gives us the isomorphism. So here, as so far we've just stated that these two groups are isomorphic. These two groups are isomorphic, but we do not specify the isomorphism explicitly. So the theorem says that the isomorphism, which for both of these, the isomorphism is given by is the function f defined as f of x equals x mod p and x mod q. So if I look at this function f with this as a domain and the codomain as this set, then the claim is that this is an isomorphism. Similarly, if I look at the function, same function f, but now I look at uh, a smaller domain, Zn star. Zn star is a strict subset of Zn because 0 will never be in Zn star. So if I look at f with domain Zn star and codomain is this, then this will also be an isomorphism. So f has to be a bijection first of all, which means that it's 1-to-1 and onto. 1-to-1 means that if you take two distinct elements in Zn, the result of this mapping in this Zp cross Zq should also be distinct. Similarly, here, if I look at, if I restrict the domain to Zn star, the result of this mapping should be, first of all, it should fall in this codomain. It can't go outside Zp star. So I can't have an x which belongs to Zn star, and then when I take x mod p, it should not be an element which is outside Zp star. So it has to be in Zp star. So this mapping is not only, it is defined on this, and it should be 1-to-1 and onto. So distinct elements in Zn star will map to distinct ordered pairs in this set and onto. So for every ordered pair in this set, there is a pre-image in this set. Similarly, for every ordered pair in this set, there is a pre-image in this. Okay, so we'll prove this, and let's see how this will work. Let me turn the page now. So before we prove the Chinese remainder theorem, let's look at an example. So let's consider n equals 15. So p is 3 and q is 5. So they both are integers greater than 1, and the GCD of 3 and 5 is 1. So the hypothesis of the theorem are satisfied. So what does it saying? So Z15, which is going to be 0, 1, 2 up to 14 with modulo 15 as the binary operation, is isomorphic to Z3 cross Z5, which is the set of ordered pairs with the first coordinate from Z3 and the second coordinate from Z5. So the first coordinate Z3, let's take 0, then 0, 0, 0, 1, 0, 2, 0, 3, 0, 4, then first coordinate we can take 1 and 0 and 1, 1, 1, 2, 1, 3, and 1, 4, and finally 2, 0, 2, 1, 2, 2, 2, 3, 2, 4. So the Chinese remainder theorem says that first of all these two sets these two groups are isomorphic, where in the first group you have modulo 15 as operation, and the second group you have coordinate wise mod 3 and mod 5 as operation. Okay. So let's look at an example. Let's take 5 and 9. Maybe we'll have some overflow. Yeah, 5 and 9 and in Z15. So let's look at that. So 5 is going to be mapped to, I'll use notation for the mapping. So this means that 5 in Z15 is going to be mapped to something in Z3 cross Z5. So we said first coordinate mod 3, second coordinate mod 5. First coordinate mod P and mod Q, right? So this is 5 mod 3 is 2 and 5 mod 5 is 0. Yeah. And 9 is going to be mapped to 9 mod 3 is 0 and 9 mod 5 is 4. Okay. Now 5 plus 9 in the first group Z15 is 14. So that is mapped to 14 mod 3 is 2 and 14 mod 5 is 4. And you can see that this is equal to 2 comma 0 plus 0 comma 4. So the f of 14 is f of 5 plus f of. Okay, so that's the example. So we are just looking at the first part of the Chinese remainder theorem. Z15 is isomorphic to Z3 cross Z5. So we just looked at one particular choice of pair of elements from Z15, and we are making sure that the mapping is faithful to the claim of the theorem. So now let's look at Z15 star. So that consists of elements from 1 to 14 which have GCD 1 with 15. So 1 is definitely one of them. 2 is an even number, and it has GCD 1 with 15, so 2. Then 3 does not have a GCD of 1, so we'll skip that. 4 has a GCD of 1. Then 5 doesn't have a GCD of 1, we'll skip that. 6 doesn't have a GCD of 1. 7 does. 8 doesn't have a GCD of 1. 9 doesn't have a GCD of 1 with 15. 10 doesn't have a GCD of 1. 11. Oh wait, 8, we skipped it. 8. 8 has a GCD of 1. And then 11. I keep going, you see, find that this is the set Z15. So the integers from 1 to 14 which have a GCD of 1 with 15. Okay. And Z3 star is going to be just 1 and 2, because in the last lecture we saw that when the modulus is prime, 3 is a prime, so then ZP star will be all the integers 1 to P minus 1. So Z3 star is that, and Z5 star is similarly 1 to 4. So now Z3 star cross Z5 star will be these 1, 1, 1, 2, 1, 3, 1, 4, and then 2, 1, 2, 2, 2, 3, 2, 4. This is the set. So the claim of the Chinese remainder theorem is that this Z15 star is isomorphic to Z3 star cross Z5 star. So let's take two elements. Let's take 8 and 13. Okay. Now remember the operation is multiplication modulo 15. So, but the mapping is what 8 is mapped to. The mapping is the same mapping as the previous case. It is modulo 3 and modulo 5. So 8 mod 3 is 2, and 8 mod 5 is 3. 13 is mapped to 13 mod 3 is 1, and 13 mod 5 is 3. Now this 8 times 15, 8 times 13, sorry, 8 times 13 mod 15. So I'm doing the operation first in Z15 star. 8 times 13 mod 15 is going to be 104, right? 8 times 3 is 24, 8 times 10 is 80, so this is 104. 15, so this is 15 is, so this is 104 mod 15. 15 times 6 is 19, so we get, this is 14. Now let's look at the mapping of 14 will be 14 is 14 mod 3 is 2, and 14 mod 5 is 4, so it's 2 comma 4. If you look at these guys, now if you multiply them coordinate wise, so 2 comma 3 1 comma 3 is going to be 2 mod 3 and 9 mod 5, which is 2 comma 5. So if you see that, so f of 8 times 13 is going to be 2 comma 4, and then f of 8 is 2 comma 3, f of 13 is 1 comma 3, and you take the product, you get the same 2 comma 4. Okay. So now let's do the proof of the Chinese remainder theorem. So proof of CRT. So first let's do Zn. So we have n equals pq, and p and q are greater than 1, integers greater than 1, and the GCD of p and q is 1. And we want to argue that Zn is isomorphic to Cp cross Cq. Okay, and the claim of the theorem was that this mapping works. F of x equals x mod p x mod q. This is an isomorphism. So we want to show that first of all that if this function defined on Zn is a bijection. So we have to show that it is 1-to-1 and onto, and then we have to show that we need to show two things. First, f is a bijection. Second, f of x plus y mod n is, that is, the if you do the operation of any two arbitrary x and y in Zn, the result of that is f of x circle f of y for all x, y, and z. So this circle is going to be the coordinate wise addition operation in zp cross zq. So this so let me just write that explicitly. F of x where f of x circle f of y is going to be x mod p x mod q plus y mod p y mod q. Okay. So here it will be coordinate wise addition, and then we have to reduce it modulo p in the first coordinate and reduce it modulo q in the second coordinate. So we need to show this. So this will be easy to show. The second part is easy to show. Let's argue the first part. So this I will not do. So because this is just a manipulation and you can check that it works out. So let's do this. F is a 1-to-1 and onto function. So to prove that it is 1-to-1 and onto, we'll only prove that it is 1-to-1. Okay. And we'll argue that the domain and the codomain, they have the same cardinality. So this n is equal to pq. So the domain has range, domain has cardinality n, and the codomain has cardinality p times q, because this has these are the integers 0 to p minus 1, these are the integers 0 to q minus 1. So there are p elements in this and q elements in this. So it's a Cartesian product. So it's the codomain also has cardinality n or p times q. So when you have the domain and the codomain have the same cardinality, if you have a 1-to-1 function with this domain and codomain, then it has to be onto, because if 1-to-1 means that if for any two integers x and x prime in this Zn, f of x is not equal to f of x prime. So if all the images of the integers in this set are distinct, then they will cover n ordered pairs here, and there are only n ordered pairs in this set, so we would have covered all of them. So onto follows from the fact that the domain and the codomain have the same number of elements and the function is one to one. So we just will show that it is one to one. So we want to show that for x prime in Zn, we want to show that f of x equals f of x prime implies x equals x prime. So if the images with respect to this function f are equal, then the pre-images have to be equal. That is, the arguments had to be equal in the first place. Okay. So let's consider this. So what is fx and what is f of x prime? So f of x is x mod p and x mod q. That is equal to x prime mod p and x prime mod q. So we have this. So this implies that x equals x prime mod p, which implies p divides x minus x prime. Because if these two are, the remainders are equal, modulo p of x and x prime, the remainders of x and x prime, the remainders when you divide by p are equal, then the difference must be divisible by p. Similarly, x equals x prime mod q implies q divides x minus x prime. So now recall that there was a proposition we did in lecture 13. I think it was 8.4. I think it's 8.4 in the text. So it says that if A divides n and B divides n, and where a and b are integers, of course, and the GCD of a and b is 1, then a times b divides n. And we'll use this proposition because with this p and q have a GCD of 1. So the, and instead of a consider, so instead of n capital N we have x minus x prime. So p divides x minus x prime, q divides x minus x prime, and GCD of p and q is 1. So p times q divides x minus x prime. So we have, so by this proposition, p times q divides x minus x prime. Okay. So we have pq divides x minus x prime, where x and x prime belong to Zn, which is the integers from 1 to 0 to n minus 1. And n is product of p and q. Okay. Now let's look at x minus x prime. So x minus x prime will belong to some range of integers because x and x prime belong to the Zn. So what is the smallest value x minus x prime can take? I want x to be as small as possible and x prime to be as large as possible. So x prime as small as possible is 0, and x prime being as large as possible is n minus 1 or pq minus 1. So it is minus pq minus 1. Next largest value is minus pq minus 2, and so on up to minus 1, 0, then 1. What is the largest value x minus x prime can take? X should be as large as possible. So the largest value is n minus 1 or pq minus 1, and x prime should be as small as possible. Smallest value is 0. So 1, 2, 3 up to PQ minus 1. So now what we had so far is that PQ divides x minus x prime. But if you look at this range here, PQ can divide 0, but PQ cannot divide any of these positive integers because all of them are strictly less than PQ. Similarly, PQ cannot divide any of these negative integers because they're all their modulus is strictly less than PQ. So the only way PQ can divide x minus x prime is if x minus x prime is equal to 0. So this implies, so PQ divides x minus x prime implies x minus x prime must be 0, which implies x is equal to x prime, which is what we wanted. We wanted to show that we wanted to show that f of x equals f of x prime implies x equals x prime, and we have shown that. We started with this x mod p x mod q equals x prime mod p x mod q, and then we got that x should be equal to x prime. So we have shown that f from Zn to Zp cross Zq is 1 to 1. And since Zn and Zp cross Zq have the same cardinality of p times q, f must be onto. So f is a bijection. So it's 1 to 1 and onto. So we have shown the first part of the Chinese remainder theorem. So we have shown that f is a bijection, and I said that I'll skip this part. So we are not showing this. So you can show that f of x plus y mod n equals f of x plus f of y, where this plus is, or we use circle, I think, in the notation circle, where circle was the operation in Zp cross Zq. So you can show this. So together with f being a bijection and this identity holding for all x, y, and zn, we have that zn is isomorphic to Zp cross Zq. Okay. Now we want to show the second part of the Chinese remainder theorem. So we want to show that Zn star is isomorphic to Zp star cross Zq star. Okay. And the way we want to show it is we want to argue that the same mapping f of x is x mod p x mod q is an isomorphism between these two groups. Okay. Now, first of all, we have to show that f is has codomain zp star times zq star. So what does that mean? If I take some arbitrary element in Zn star, it's an integer, and I compute x mod p and x mod q, where x is that integer, how do I know that the GCD of this x mod p with p is 1? So the question is that does, when x belongs to Zn star, does x mod p belong to Zp star and x mod q belong to Zq star? So what are these P and Q? Note that they are not primes, there are some integers which are relatively prime. So it may happen, it's possible that x mod p belongs to zp. It will definitely belong to zp because it's going to be some integer from 0 to p minus 1. Yeah, it's going to be some integer from 0 to p minus 1 because it's a remainder. But how do we know that it belongs to zp star? That is the GCD of x mod p with p, is it 1? Similarly, is the GCD of x mod q with q, is that equal to 1? So we have to actually show this, because to claim that f is a bijection from Zn star to Zp star cross Zq star, first of all I have to make sure that this is the right codomain. That is uh, the mapping of x by f should not fall outside this set. So I have to actually show that I have to answer yes to these two questions here. I have to show that the GCD of x mod p with p when x is in Zn star must be 1, and when x is in Zn star, the GCD of x mod q with q also should be 1. So we want to show this statement. We want to show that if x belongs to Zn star, then GCD of x mod p and p is 1, and GCD of x mod q and q is 1. And of course, we are given that p and q are relatively prime. GCD of p and q equals 1. So there was a lemma which we proved, I think, in lecture 13, which said that if x is equal to kp plus r, where all these are integers, then the GCD of x and p equals the GCD of r and p. In other words, GCD of x mod p and p. So here, if you divide x by p and you get some remainder, the GCD between x and p is going to be the same as the GCD between p and r. So here we want to show that the GCD of x mod p with p is 1, it's enough to show that the GCD of x with p is 1. Okay, and what do we know? X belongs to Zn star, so we know that GCD of x and n is 1, and that means that we can write 1 as a integer linear combination of little x and capital N. Okay. And x is little x is some k times p plus r, whereas r is x mod p plus y times n. So here I will expand n as pq, and I will collect the terms which involve p. So xk here, and then yq. Here I have xr. So we have written 1 as an integer linear combination of p and r, which means that the GCD of p and r is 1, because the GCD of two integers is the smallest positive integer, which can be written as a linear combination of those integers. So this implies that the GCD of P and R is 1. So actually we didn't need to use the GCD of, we didn't show this, we actually showed this GCD of P and R is 1 directly. And the proof for showing that the GCD of Q and R is 1, or not, I should not say R, because R is X mod P. So similarly we can show that the GCD of X mod Q and Q is 1. So this implies the GCD of X mod P should say, okay, this R was on this side, so I apologize for that. So this is X mod P, so the GCD of P and X mod P is 1. I should have written that, but this is also fine. So similarly we can show this. So what we have shown is this mapping here, F from Zn star, is actually has codomain Zp star times Zq star, where f of x is X mod P, X mod Q. Okay. So it's so writing this is, it's well defined. It's correct, because we have shown that if you take some arbitrary element in Zn star and you apply this function here, the result will actually lie in Zp star cross Zq star. It will not go out of it. Okay. But we wanted to show more. We wanted to show that this is in fact a bijection. So we can try to use the same strategy as before. So let's first show that it is 1-to-1 and then see where that takes us. So let's consider for x prime and Zn star, suppose f of x is equal to f of x prime. Okay. Now in the previous part of the proof, we already showed that this implies x is equal to x prime, because we showed that f is 1-to-1 when you look at even the larger set, when you look at Zn, and if the images agree, images of two elements agree, that is if f of x is equal to f of x prime, then x is equal to x prime. So since Zn star is a subset of Zn, so that condition will hold here as well. So then we do get x is equal to x prime. So we have 1-to-1 even in this situation. So the mapping itself doesn't involve any addition or multiplication. You might say that, okay, though that Zn was the group operation was addition modulo n, and now Zn star is multiplication modulo n. But here we are only talking about the one-to-oneness of the map, and that since it holds in the larger set Zn, which contains Zn star as a subset, it will hold in the subset as well. So this function is 1-to-1. But is it onto? So now let's look at the codomain here. What is the cardinality of the codomain? What is the cardinality of the domain? So the cardinality of the domain is phi of n. Where phi is the Euler phi function, which is phi of pq, because here we have that p and q, n is equal to pq, where p and q are relatively prime. Now what is the cardinality of the codomain? It's phi of p times phi of q. Okay. Again, recall, even though the notation it may be misleading because we were using p and Q for primes. But here in the hypothesis of the Chinese remainder theorem, P and Q are some arbitrary positive integers which are relatively prime. So it is not, we can't say it's P minus 1, phi of P is P minus 1 and phi of Q is Q minus 1. It is phi of P and phi of Q. P and Q are some integers, positive integers greater than 1. So we have a function which is 1 to 1. If we can prove, or if we could have argued that phi of pq is equal to phi of p times phi of q, then we would be done. As in the previous case, you have a 1 to 1 function where the domain and the codomain have the same cardinality, and by that it is onto, and we would say that f is a bijection. But we did discuss this result. We said that when p and q are relatively prime, phi of pq is equal to phi of p into phi of q. But that result is actually, we said that it follows from the Chinese remainder theorem. Phi of pq equals phi of p into phi of q for when GCD of p and q is 1. This result actually follows from the Chinese remainder theorem. So we can't use this result to prove the Chinese remainder theorem because it will be a logical fallacy. So let me repeat that again. We proved that the function is 1 to 1. If we could have argued that the domain and the codomain have the same cardinality, we would have shown that the function is onto as well. The domain has cardinality phi of pq. The codomain has cardinality phi of p into phi of q. Now this identity holds, but the proof of this identity is the Chinese remainder theorem, because once we are done with the Chinese remainder theorem, that it implies that this phi of n is phi of p into phi of q. So this identity is, we said we'll prove it using the Chinese remainder theorem. So we can't use this identity in the proof of the Chinese remainder theorem. That will be like a circular argument. So we will prove that this function is onto without using this cardinality argument. So we showed that it is 1 to 1. Now I'll just show that it is onto. That is, for any element in this Zp star cross Zq star, there exists a pre-image. There exists an element in Zn star which maps to that ordered pair. Okay. So I'll not use the cardinality argument, and I'll prove that this mapping is onto directly. So we want to show this in this statement. So we want to show that f from Zn star to Zp star cross Zk star is onto, which means that for every ordered pair in this set, we have to find an x in Zn star such that f of x, which is given by this x mod p, x mod q, is equal to that ordered pair AB. So note that we have shown that when we remove these stars, that function is onto. So if you have some ordered pair in Zp cross Zq, then we can find a pre-image. So one can ask, why can't we use that argument? So we already know that f from Zn to Zp cross Zq is onto. Why can't we use this as Zp star cross Zq star is a subset of Zp cross Zq? The thing is that this is onto. So for any ordered pair in this, there will be a pre-image, but there is no guarantee that that pre-image will fall in Zn star, because Zn star is a subset of Zn. It can the pre-image according to of this function, it could happen that if I take some element here, that element also belongs to this, so that should have a pre-image. But what if that pre-image falls outside Zn star? So we have to actually show that the pre-image of any ordered pair in Zp star cross Zq star, we already know it falls in Zn, but does it actually belong to Zn star? That is the part we have to actually do. So let's do that. Okay. So let's let AB belong to Zp star cross Zq star. Since f is a bijection from Zn to Zp cross Zq, and AB belongs to Zp cross Zq, because this is a subset of this. So F is a bijection from Zp to Zp cross Zq. There exists an X in Zn such that f of x is equal to AB. Okay. But what we want to now show is that we want to argue x belongs to Zn star. So that x which we got as a pre-image of f on AB, that actually belongs to Zn star. So that is, we want to show that the GCD of x and n is 1. Okay. So now x belongs to Zn, so it belongs to from 0 to n minus 1. But if x was 0, then the GCD of 0 and n would be n, because the n is a product of p and q, and we said p and q are greater than 1. So by showing this, we are showing not only that the GCD is 1, we are also showing that x is not 0. So x belongs from 1 to n minus 1, and the GCD is 1. Okay. So this will show that x is in Zn star. Okay, so what do we know? We know that GCD of P and Q is 1. So this implies 1 can be written as some capital X times P plus capital Y times Q for some integers X, Y, and Z. So we also know that AB belongs to ZP star cross ZQ star. We know this. So which means the GCD of A and P is 1. But what is A? A is actually X mod P, because we said that consider an X such that f of X is equal to AB. So which implies the GCD of X mod P, and P is 1. Now the GCD of X mod P and P, by the lemma we saw in lecture 13, it's equal to the GCD of X and P. And so this implies there exist integers capital A, capital B, such that 1 is equal to capital A times little x plus capital B times little p for some capital A, capital B in Z, the integers. Similarly, GCD of B and Q is 1, because we said that AB belongs to ZP star cross ZQ star. So ZQ star is precisely those integers B such that the GCD has to be 1 with Q. So this again by the same argument. So the GCD of B mod Q and Q is 1. So X mod Q is 1, which implies GCD of X and Q is 1, which implies 1 can be written as a linear combination of X and Q. So CX plus DQ for some CD in Z. So we have these three equations here. One can be written as xp plus yq, one can be written as ax plus bp, one can be written as cx plus dq. So I'm going to use that to prove what we want. So finally, what we want is we want to show that GCD of x and n is 1. So if I can write 1 as an integer linear combination of x and capital N, I'm done. That's what I'll try to. So say 1 is xp plus yq, because GCD of p and q is 1. I can write this as xp times 1 plus yq times 1. This is xp into, replace the 1 with cx plus dq, because I want to get the product pq, and pq is n, so I want to do that, and yq into ax plus pp. This is x capital CP plus y capital AQ into x. So I took this. So this term here contributes this. This term here is contributing this. And P times Q, that will become N. So XD plus YB P times Q. So this XP dq is the xt term here into pq, and here it is yb. So this is some integer linear combination of x and n, and this implies that the GCD of x and n is 1. Okay, so we have shown that f is actually onto. So it's 1-to-1 and onto, hence it is a bijection. And to show that these two groups are isomorphic, we have to still check that if I take two, I have to check that f x times y mod n is fx fy, where when f of x is the mapping into this group, f of y is the mapping into this group, and you do the coordinate wise multiplication modulo p and modulo q, then you get the same answer. So we have to check this, so I'm going to skip that, so it is easy to check. It's just some mechanics. So this completes the proof of the uh, Chinese remainder theorem. CRT. And so now we can the corollary is that the Euler phi function is multiplicative. So for integers m and n, such that m greater than or equal to 1, n greater than or equal to 1, and GCD of mn is 1, phi of m times n is equal to phi of m into phi of n, where phi is the Euler phi function. So in the Chinese remainder theorem, we wanted these integers to be strictly positive, but recall that when you have the Euler phi function, if m is equal to 1, phi of 1 is 1. So if either of these or both of these are 1, then we'll just get a trivial identity. So for the non-trivial case where both m and n are both greater than 1, then we appeal to the Chinese remainder theorem. We say that Zmn star, the proof is just one line, Zmn star, or I should say that for m equals 1 or n equals 1, the result is trivial. because you just have, if n equals 1, you just have phi of m, and phi of 1 is 1, so phi of m is equal to phi of m. So it follows trivially. But for both m greater than 1 and n greater than 1, it follows from the Chinese remainder theorem. Because the cardinality of this is phi of mn, and the cardinality of this is phi of m, cardinality of this is phi of n, and the cardinality of this is just the product of this, because it's a Cartesian product. Okay. So this ends part 2 of lecture 16, and then we'll look at some applications of Chinese remainder theorem in the next lecture. Thank you.